All right, part 2, which I'm recording at the exact same time. And we're going to hope that first video went just fine. So current in an LC circuit. So last time we did RL circuits, now we're doing LC circuits. So RC circuits. Slow approach to equilibrium. We watch light bulbs dim many times. And our L circuits, there's a slow approach to steady state. What if you put them together? Then what might happen? Well, then you'd get a circuit that looks like this. You have an LC circuit, which consists of an inductor and a capacitor. Your LC circuit. All right, so there's some very interesting things that these circuits can do. So LC circuits are capable of oscillating back and forth and never reaching equilibrium or steady state, if R is small. If they've got some resistance on them, they will dampen. All right, so if you connect a charged capacitor to an LC circuit, so your capacitor is charged up. It is ready to be discharged in a circuit. And we know what that looks like. So immediately, the current is slow to start, the inductor opposes attempts to change current, all right, and then eventually if you're persistent enough, the current will change and the capacitor will lose charge. And this, of course, eventually Q will be equal to 0. Okay, so then it runs down, right? Well, remember, however, the inductor can't just go to 0. No, That's a huge di dt resulting in a huge dB dt resulting in a huge EMF. So it overshoots. The equilibrium and dumps charge on the capacitor. So you got all that EMF, goes right back there. And the process repeats. Going back and forth and back and forth. Charging up the capacitor, discharging the capacitor. And what we'll see is that you can relate this to the energy, and so you've got energy stored in the capacitor, energy stored in the solenoid. Okay. If there's no resistance, it goes on forever. It's the current that goes on and on, my friends. Some people started oscillating it, not knowing what it was, and it will oscillate forever just because this is an LC circuit with no resistance. Some people connected it not knowing what it was. But that won't be you. Oh, I've been doing this too long. All right, so the energy conservation loop rule for this circuit is as follows. Delta V capacitor plus delta V inductor equals 1 over CQ minus L di dt is equal to 0. Q is the charge on the upper plate of the capacitor, and I is conventional current. Further, I is equal to minus dq dt. We talked about this a little bit before, but it's basically dq dt is charge flowing off the plate. So you have coulombs per second, which is the same as current. And so we can use this relationship. And so 1 over CQ plus L di dt becomes 1 over C plus L d squared Q over dtt squared. So you have the double derivative of Q with respect to time is equal to 0. All right, one solution. There's a couple solutions that works for Q, but the one that we will focus on is Q is equal to Qi cosine 1 over LC T. And this works if you plug that into there and take the second time base derivative. And 211, you should totally do that. We can also see both classes. We can see that it satisfies. So if t is equal to 0, the initial condition, then Q is equal to Qi cosine of 0, which is equal to Qi. So we can at least see that, that it satisfies that condition. All right, so we can use this to calculate current. So I is equal to minus dq dt is equal to qi over the root of LC sine 1 over root LC times time. Graphically, what we're looking at would look something like this. So we can plot where this is charge, Q is equal to Q naught cosine 1 over LC times T. And then I can use current. Oh, I'm not doing a great job of that. Ooh. So you have I is dq dt. And you can see that there's that ramp up there. Now, if this is, of course, assumes R is negligible. If R is not negligible, you would see this dampening effect for both of them. I'm not going to, I've already botched one, I'm not going to go for botching two. So, the period of oscillation is T is equal to 2 pi LC, and the frequency is equal to 1 over T is equal to 1 over 2 pi root LC. So energy in an LC circuit so I kind of hinted at this before. Another way to look at LC circuits is to look at it in terms of where the energy is stored. So the original energy, the OG energy in LC circuit is in the capacitor. I've missed my calling in life. I knew I should have been a rapper. All right, is Q Q squared over 2C. And you can go back to chapter 19 to see that. All right, so when the charge on the capacitor goes to 0, all energy is in the inductor. And so the magnetic energy stored in the inductor is 1/2 Li squared, which we just talked about magnetic energy. So at T equals 0, I equals 0, magnetic energy is 0. So all energy is electric. Boogie, woogie, woogie, woogie. And when Q equals 0, I is maximized. All right, so what we're going to do is we want to get some useful handy-dandy equations. Let's use Qi as the initial charge and find I max. So, stored energy at T equals 0, it's all electric. So U is equal to U electric plus U magnetic is 1/2 Qi squared over C. And when I equals I max, Q is equal to 0. And then we have all magnetic stored energy. So U is equal to U electric plus U magnetic is equal to 1/2 Li squared max. And because of the energy principle, the total energy of the circuit is not going to change. Total energy does not change. It just gets moved around a bit. Therefore, 1/2 Li squared max is equal to 1/2 Qi squared over C. I max, the better I max, is equal to Qi over LC. And there you go. Now you have a term for the maximum current in terms of the initial charge on the capacitor plate. So let's do an example. An LC circuit has a 50 millihenry inductor and a 40 microfarad capacitor, and we want to know the frequency, and if Q max is equal to 100 microcoulombs, what is V max? So, frequency, 1 over 2 pi root LC is equal to 1 over 2 pi, 50 times 10 to the minus 3 Henry times 4.0 times 10 to the 5 coulombs. Frequency is equal to 112 hertz. And V max, think back to chapter 19, is equal to Q max over C is equal to 100 microcoulombs over 40 microfarads. Because they're both micro, I'm not going to unit convert, and this is equal to 2.5 volts. And what is the maximum energy in this setup? Well, we just talked about that. That would be 1/2 Q squared over C is equal to 1.0 times 10 to the minus 4 C squared over 2 times 4.0 times 10 to the minus 5 farads is equal to 1.25 times 10 to the minus 4 joules. And there you have it. So that wraps up chapter 22. Next lecture, we will start to dig into chapter 23. And yes, we will see energy density once again.